Okay, so the interpretation of the question we're taking on question 2 is you have a 2025 by 2025 square, and you're allowed to sort of take like smaller squares to check if there's anything inside the smaller square. Okay, so that's what we mean by like a checkered square inside. So the only condition is this blue square can't be like the whole red square, right? So there's meant to be some sort of like cells which are marked. Maybe like you can think of it as like Minesweeper or something. There's mines in a bunch of cells, and then you get to sweep this blue square. And it's sort of how many but the sweep doesn't tell you which cells have mines in it. It just tells you the total number of mines in the whole area, right? And then the question is like how many sweeps do you need to determine the total number of mines in the whole red square, yeah? Okay. So people managed to come up with some pretty good constructions. So you could have you have your 2025 square, and you could sweep like, for example, all but one. You could do a 2024. That could be your first sweep, yeah?
Yeah.
Okay, and then your second sweep could be like this 2024 by 2024. Okay. And then you can have your last 3 sweeps be like here. So here, here, and here, yeah? So basically what you get is, so the 2 big sweeps overlap in the middle square, and then you know what the overlap is exactly, so you can calculate how many sort of mines are in everything except the 2 corners, right?
Yeah.
And then once you get the 2 corners, you know exactly what's in the whole thing, right? So it's a pretty straightforward way to get like the 2 marks of the construction, yeah? There's obviously lots of variations of this. You can have it just overlap at 1 cell in the middle or something, you know? Okay. If you have, so you've done that. Now you need to prove why you can't do it with less than 5, right? Okay. And you know, we saw a bunch of attempts, but there are some methods you can kind of just, they're just clearly better than others, okay? Alright. So, for example, people will say that there need to be at least 4 squares, right?
Yeah.
So one way to say that is, you could say the corner cells, right?
Yes.
Yeah. So you first say like for your thing to work, you have to at least cover all the cells, right?
Yes.
As otherwise having something uncovered, if there is a marked one, if there's not marked one, it's the same, but the count's different, right? The count's the same, but the situation's different, yeah? Okay. So to get the 4 corner ones, right? Like to get a corner one, it can't get any of the other corner ones, right? So each corner belongs to at most one blue square, because the blue square is not allowed to cover the whole thing, right? Does that make sense? Is that what you did?
Yeah.
Yeah, you had a lot of good things in yours too. It's just, I think it's just one minor problem still, same as the others. So this proves you need at least 4 squares, right? Yeah. Okay. Now you want to prove
That you can't do it in 4 squares.
you can't do it with 4 squares, right? Yeah. I mean, there were still some other ideas that were kind of nice as well. Like, you know, like the top row can't be gotten at the same time as the bottom row, right? And you can't get the top row in just 1 square, right? So you need 2 squares to get the top row, and those 2 squares don't have anything in common with the bottom row. So you need another 2 squares to get the bottom row, yeah?
Okay.
Okay.
So wait, how exactly do you achieve that?
Huh?
Because if you do, then you create a 2025 square, and that's
So like,
So nothing.
yeah, so you can't have all the cells in one row because a square can't be that long, right?
Yes.
Okay. So if you combine these ideas, like, I think the problem is most people just kind of discarded these ideas and just started a new argument for why it can't be 4. And then they just said that, like, oh, overlaps are bad, so we just prove that there are overlaps, and once there are overlaps, it's finished, right? But you have to also prove what happens when there are overlaps, yeah? So maybe let me demonstrate. So you can kind of say, like, suppose we have 4 squares,
Then we are guaranteed an overlap.
does the job, yeah? So suppose 4 squares determines the total. So if that's the case, see, the thing is, we know that each corner has to belong to a separate square, right?
Yeah.
So we can actually assume the 4 squares are all cornered. You know what I mean? The 4 squares are like, they all go into the corner.
Oh, that looks so trippy.
Does that make sense? And a lot of the time, the argument that's kind of confusing is like, when there's an overlap, right? You're just saying and then most of the time no one says anything. But if they say something at all, they say like, oh, if there's an overlap, you need a 3rd square to deal with it, right? But the thing is, we have 4 squares, right? That doesn't show the other 2 squares aren't dealing with it. You know what I mean? Okay, so maybe the clean way, not necessarily the shortest way, but so what you can do is you can assume there's an overlap. Like if there's 4 squares in the corner, right? There's only 2 kinds of overlap you can have, yeah?
Okay.
There's like the overlap between squares like on the edge, right?
Yeah.
And then there's the overlaps. So that's also the same as like that kind of overlap between these squares, yeah?
Yeah.
And then there's the kind of overlap that is like a diagonal between the squares of the opposite corners, right? So you could prove them separately if you wanted to, right? So you go like assume that there's an overlap like this, yeah? Does that make sense?
Yeah.
So we can prove that this overlap doesn't exist, yeah? Or can't exist, yeah? How do we prove that? You see? Yes?
The square on the top that overlaps the top edge.
Yeah, exactly. So you can put a marked cell here, okay? Okay. And what do we know about that marked cell? So imagine the situation where.
Oh, we don't know anything currently.
So imagine the situation where you just have the blue cell marked, yeah?
Yeah.
Then both the squares detect it and they count 1 and 1, right? Yeah? Okay. And so both squares are yes and yes, right? And both the squares on the below can't reach the top row, right? Yes? Hello?
Yeah.
So both the bottom squares, because they have to touch the bottom corner,
Yeah.
they touch the bottom row, so they can't touch the top row, right?
Yes.
So they can't reach that cell, yeah?
Yeah.
So this cell's only covered by these 2, yeah?
Okay.
Does that make sense?
Yes.
Okay, so then when you just have a blue marked cell here, right? Then the 4 squares will say yes, yes, no, no, right? Yeah? Okay, and whatever that means, there's only 1 blue cell, yeah?
Yeah.
Okay, but now you could also put red cell here and a red cell here, right? Okay. And we know the red cells only belong to those 2 squares, right?
Yeah.
So then those 2 squares again will say yes, and the other 2 squares again will say no and no, right?
Yes.
So it's exactly the same detection, but you have 2 marked cells and you had 1 before. Does that make sense?
Yeah.
So this did not successfully determine for sure the number of marked cells, right?
I see.
Can you see how the difference between that as a proof and what the other stuff we saw was?
Yeah.
There's no doubt here, right? You can bet your house on this. Whereas before you weren't even willing to maybe bet your lunch on it, you know?
Yeah.
Okay, so So now we can assume there are no edge overlaps like this, right? Does that make sense?
Okay.
Okay.
And then
So sometimes a long proof isn't necessarily a bad proof, you understand?
Yes.
Because the goal is to be sure, yeah?
Yeah.
Okay, so we have now we have no overlap, yeah? But we do know that, like, it has to cover the first row, right?
Okay.
So it has to be something like this, yeah? Right? Does that make sense? And one of them is going to be like more than half,
Okay.
and the other one's going to be less than half, right? So, okay. Does that make sense? But actually having that actually also determines sort of what the size of the other squares have to be as well, right?
Yeah, because they can't edge overlap.
So this actually forces it to be here, yeah? Right?
Yes, it does.
Right? Because it can't edge overlap and it has to cover the whole last column, right? Yes? Okay, and then that forces this. That forces this to be the last square, right?
Yes.
Does that make sense? So now we have a very like explicit picture, right? Okay, so what can we do here? How do we prove this cannot work?
Because of the middle part.
Yeah, it's because there's an overlap, but what I'm trying to emphasize here, it's not just that there is an overlap, I'm actually also telling you how to prove that the overlap fails, right? You understand? So consider a board where only this is marked, right? Yeah? Okay?
Oh, that's confusing.
Yeah.
Oh, I see.
Or something in here is marked, right?
Yeah.
Then this will say no, this will say no, and this will say yes, and this will say yes, right? Okay?
You can't conclude anything though.
Yeah, but then you take that out and you put back the corner cells again, right?
Yeah, it gives you the same data, so you can't be sure.
So now you have the same same output, right? But you have a different input. You understand? So it's like the function isn't 1-to-1 or whatever. Like you can't tell the difference between. So here there's two marked cells, right? And before there's only one marked cell. But the mine detectors all give you the same info, yeah? So can you see how that proves for sure? It's like who's sure in this determination for sure? So basically it's me that's sure now. Okay? Okay, so I can say for sure that with this interpretation of the question, I need at least 5, right? And I can do it with 5. Does that make sense? You guys have any questions? Any questions? Okay.